Hey everyone, Amin here with AI Plays. Today we're covering black level compensation. Let's get started. To recap from the previous video, we mathematically computed the location of dead or otherwise broken pixels and adjusted their values in the image. Now before we start with black level compensation though, I would like to address a comment from Raries on the previous video asking if there is a faster way to perform these operations. The answer is absolutely yes there is. We used one of the most brute force methods possible with for loops. In the image we are using, there are 24,587,520 different pixels. We checked each one individually, then ran if conditions and ran various computations throughout. Again, terribly inefficient. The reason I did it this way is because it's also the easiest to understand. My goal in these videos is for anyone with even just a basic level of computer programming understanding to be able to follow along and understand how a camera can work. I will, however, be posting the code for a fast image signal processing pipeline on my GitHub, along with the ISP we work on together in this series, both linked in the description below. It uses slightly more advanced NumPy slicing and vectorization techniques, and if there's interest, I'm more than happy to make videos detailing how the faster versions work. For a performance comparison, the dead pixel concealment we did in the previous video took about 10.5 minutes to run. This faster dead pixel concealment takes about 1.5 seconds. As for real cameras, the image signal processor is a piece of hardware which lets it perform very few but very specialized operations very quickly. The ISP we are building is in software, and even the fast ISP I have on GitHub is not fully optimized. Now let's get started with black level compensation. The idea behind black level compensation returns to how CMOS sensors work. If you remember from the first video in the series, light strikes a photodiode, and through the photoelectric effect, electrons escape into the potential well, sending a voltage signal. The returned voltage value for a pixel that is supposed to show the color black should be 0. But there will always be light falling on every single pixel when a picture is taken, and unless the pixel in question is dead, the returned voltage signal cannot be 0. Black level compensation subtracts a certain offset from each channel in the entire Bayer image, such that areas that are supposed to be black actually show as black in the final image. This is the formula for black level compensation. The compensated pixel value is the original pixel value minus a certain offset. And since the offset is due to the power of the sensor, it is the same every time and can be stored in the camera's internal memory. Now let's have a look at the code. The inputs are the DPC image we created in the previous step, and a dictionary holding the information on all of the offsets. First, we get the shape of the DPC image to iterate over. Then we make a blank array of the same shape to iterate over. Now we need a method to determine if we are on a red, green on red row, green on blue row, or blue pixel, and we can do that with some clever indexing. From the image on screen, you can see that red pixels only show up when both the row and the column index are even. Conversely, if the row and column index are both even, you are definitely looking at a red pixel. To identify red pixels, all we have to do is iterate through the entire image and pick out the points where both the row and column index are even. And we can do that with the modulo operator. The modulo operator represented by the percent sign will perform a division and return the remainder. So for example, 10 modulo 3 returns 1. Since any even number divided by 2 always divides perfectly, if the row and column index modulo 2 are both equal to 0, both indices are even, and you're on a red pixel. You can then add the black level compensation red channel offset and continue scanning the pixels. The same logic applies for green on red row, green on blue row, and blue pixels. By checking combinations of even and odd row and column indices, you can determine what kind of pixel you're dealing with and how to address it. Finally, to avoid dealing with negative numbers, we use np.clip on our finalized image with 0 as the lower bound and no upper bound. What this does is if there are any negative numbers, meaning too much offset was added, you'll just set them back to 0. As for the value of the offsets themselves, camera manufacturers have methods to automatically determine the best offsets. These could involve things like taking a picture with the lens still on shortly after manufacturing and running an algorithm to compute. Usually they'll end up not having R, GR, GB, and B offsets the same. For us though, I'm just going to subtract 10, since using the np.min command, I know that the minimum value in this image is around 10. Finally, you can visualize the image using plt.imshow. Kind of like dead pixel concealment, there's Not much of a major change. And the reason for that is our image is currently in 16-bit. The maximum value is over 16,000, while the maximum possible value is 65,535. Subtracting 10 won't really make a noticeable difference to the naked eye on the scale. That's it for today. Next time we'll cover lens shading correction. Have a good day, everyone.